Hey, what's up guys? It's Eugene from Pentland Designs. Today we're going to be going over the top 5 things to think about when designing for 3D printing. Number 5, reinforcing areas. So on one of the designs that I was working on, I was making a 3D printed grocery bag holder. So how this would work is that you'd be able to open this little lever up, be able to put the grocery bags here, and then close it and carry it, and it makes it really nice and convenient, a nice grip to be able to grab onto things. The issue that I was having with this design is that this pivot point right here was the weakest point. So essentially, if you put too much force on it, the first place that it was most likely to break was the pin that holds this in place. And this is printed entirely pre-assembled. So if we take a look at the Fusion 360 model, there's a really easy way to reinforce this model without actually having to just, say, increase the infill everywhere. And the way you're able to do that is by adding small slits inside the model. So if I turn on this analysis right here, you can see right here in this section, you'll be able to see the 3 small slits that I have in here. And these are very, very thin. They're just small enough that it's going to actually trick your slicing software into thinking it's a perimeter. So essentially what that's doing is increasing the infill of one particular area without having to increase it throughout the entire model. So by doing this, I was able to meet my design criteria without having to say, increasing the infill throughout the entire model. So if you have a particular area that's going to be going under a lot of loads, or a particular area that you need to be stronger than everything else, adding very small, thin slits will make it so it's stronger in that one particular region without having to increase the infill everywhere else. And you can quickly see this by looking in Simplify 3D. This is the pin region right here. You can see it's making those small slits inside of there, reinforcing that pin a little bit stronger. Number 4, bridging. In 3D printing, bridging is when you're printing over an open area and you need to get a piece of material from one side to the next, and you don't need to have a support structure. So a good way to explain this is if you've ever used a tape measure before. So if you have a tape measure and you pull it out very short distance, it's going to be able to keep its shape. It's, the structural integrity of the tape measure from being slightly curved is going to allow it to keep going, and it's going to stay out straight. But the farther the distance that you make it go, the more likely that it is that it's going to start to bend and collapse. And it's kind of the same thing in 3D printing. If you're printing over a very small gap, it's likely that it's still going to be able to keep that line nice and straight. But if you're going from, say, one solid position out into nothing, and there's nothing else to support it on the other side, then it's going to start drooping. So bridging is when you have a big open area. So say I'm trying to print a string going across from one side to the next. But because there's a tower on one side and a tower on the other, it's able to make that line pretty much perfectly straight because there's somewhere to connect it to. So one way I was able to take advantage of this was actually in the design of this model. Like I said, this prints entirely pre-assembled, so you can see here that the pin runs all the way through the middle of here, and we're taking advantage of bridging to be able to get this to work. So after this finishes printing, all you have to kind of do is take your 3D model, snap this arm out of place, and then it is good to go. You don't have to do anything else. So you can see in this model, there's actually a tiny little gap in between these two sections. So in between the hinge and then the wall, there's a 0.375 millimeter gap. And what this is doing is allowing there to be enough space that the material is not going to stick to the previous layer, and that it's far away enough, and it's still close enough that if there were any drooping, it wouldn't droop enough to actually make it adhere to itself. So a better way to explain this and to visualize this is actually in the slicing. So this is the very last layer before that top layer starts. So if I go to the next layer, you can see it built this entire yellow region. So in this yellow region, pretty much this whole half of this section has material for it to go to. So from this point here to this point here, it could just make a single string and it has somewhere to attach to, so it'll be nice and straight, and that's where throughout the majority of the pin. And then the rest of it that's up here in this section, that's really the section where it may be drooping a little bit more and why you actually have to kind of snap it out of place to be able to get it to go there. Number 3, thin walls. Whenever you're printing a wall between, say, 0.8 to 2 millimeters in thickness, you want to have the wall thickness be a multiple of the nozzle diameter. So typically on most 3D printers, it comes standard with a 0.4 millimeter nozzle. So if you're printing thin walls, you're going to want it to be in that small range. You're going to want it to be either, say, a 0.4, a 0.8, a 1.2, 1.6, 2 millimeter thick wall. And the reason for this is that there's, since it is a 0.4 millimeter nozzle standard, it can't make any section smaller than that. So a good way to visualize this is by going to Simplified 3D, and in the back here, I have a model where it has 0.8 millimeter thickness walls, and then in the front, I have 1 millimeter thickness walls. So when I slice this model, you'll be able to see when I go through and look at the layers that these walls on this front section, this one that has the 1 millimeter thickness walls, the lines are not actually touching each other, because essentially what it's doing is it was told to make a 1 millimeter thick wall and it has a 0.4 millimeter thick nozzle. So it's making one wall on the left, one wall on the right, and then there's a 0.2 millimeter gap in the inside, and there's really no way for the 3D printer to be able to compensate that just due to the physical limitations and the nozzle diameter. So a way to get around this is by doing something like having the wall thickness be a multiple of that nozzle diameter. So if I have the wall thickness to be 0.8 millimeters, then it's going to have those two walls right next to each other. It's going to adhere properly, and it's going to be a much stronger part in the end. This is only something to think about when you're making very thin walls, like I said, 0.8 to 2 millimeter thickness in walls. And this is just because after it, say, normally does two perimeters, so after it does 1.6 millimeter thickness walls, then it's just filling the middle in with infill, and then at that point it doesn't matter anymore. Number 2, overhangs. Overhangs in 3D printing are where you're printing something and there's no material underneath it to support it. So it's kind of the opposite situation of bridging. In this case, there's, say, one section that you're building off of, and then there's nothing out to the side of it that it can actually build on top of. So an example of this is, say, this pin that I have right here. If I didn't have this 45-degree angle here, then there would need to be a support structure that's building up this entire section just to make this tiny little pin, because there's no material underneath it. Otherwise, the material starts sagging and it wouldn't come out properly. So whenever you're designing something and there's no material underneath it, since 3D printing is building layer on top of layer on top of layer, if you go too far out to the side, then it's not going to be able to, there's nothing underneath it to support it, so it's not going to come out properly. So whenever you're building up, you're going to want to make sure that if you have an unsupported region, you have, say, a 45-degree angle at least underneath it to be able to support that region. So you can see that occurs in that pin right there, as well as in these back sections that hold, this just holds an extra card inside the back of the wallet. It has these tiny little 45-degree angles that are there that aren't really noticeable for the actual design of it, but in terms of 3D printing, it makes it a lot easier. Like I said, you could use supports for this, but say if I were to have supports on this region, it were to go along this whole line right here, it would actually make it more likely to fail while printing, because it had to build a small separate support structure that isn't attached to the base, doesn't have a very large surface area that's attached to the build plate, and that could very likely break while building up to be able to support that pivot. Print orientation. When designing something specifically for 3D printing, print orientation is something that you should take into account even before you start designing the item. So here I have a model of an Amazon Echo Dot holder that I have designed. So have a quick look, think about what orientation in which you think this should be 3D printed. So when I made this, the way I actually have this being 3D printed is on its face. And the reason for this is that if I go on the section analysis, you can see I used the least amount of material as possible while making this thing. So there's only a small little 45-degree angle that's actually holding this Echo Dot holder in place, this Echo Dot in place, and then the rest of the body is entirely hollow. I could have made this so you could print this item standing up, but there would have been a few disadvantages to that. So if I printed this standing up as is, I would have needed to have material going along this whole curve here at a 45-degree angle, and then material going along here at a 45-degree angle, which would have increased the amount of material that would be required to actually make this. On top of that, the adhesion wouldn't be as good to the build plate. So there's a kind of balance that you have to find in making sure that everything could adhere to the build plate properly. So if I was printing standing up, then there would only be this small region that's attached to the build plate, which may or may not get disconnected over a long print. But if I'm to print it on this face, not only does that increase the appearance of that top surface, because that's going to be against the build plate, it's going to come out nice and clean. It's also going to increase the surface area that's attached to the build plate, make sure it adheres properly throughout the entire print, and you don't ever have to worry about it. So whenever you're designing for 3D printing, you always want to think about the print orientation and what makes the most sense for the design. There's a whole bunch of structural things that you may want to think about as well. So if I open back up the grocery bag holder, you can see this item gets printed on its side like this, and this is so that the layers are going along the XY plane, and it's actually able to be a lot stronger just due to the way that 3D printing is done. I'm not going to go in too depth about this in terms of the structural integrity of different types of parts. There's a whole bunch of videos you could find about this. If you go look in the video description, there's a whole bunch of videos from people like CNC Kitchen that go into material testing and layer adhesion, that kind of stuff. That would be a good resource for that. Well, thanks for watching, guys. If there's any other tips or tricks that you think might be useful while designing for 3D printing, please leave it in the comments below and let me know what you think. Have a good one.